In this video, I'm going to go into the Ospf designated router and backup designated router in theory and in practice and talk about why these things were developed for Ospf. So to begin with, let's go ahead and go to the whiteboard first before we go into our slides to talk about this concept. And like I frequently like to do, I'd like to contrast Ospf and EIGRP so you can see some of their similarities and some of their differences. So here we have 4 routers, and all 4 routers are connected to the same switch, and they're all in the same broadcast domain, as you can see from their IP address. So if we were talking about EIGRP as an example, router 1 would list R2, R3, and R4 as neighbors. Now let's say the R1 had an EIGRP update that it needed to send. We know that EIGRP updates go out as multicast packets. And what do switches do with multicasts? They flood them, just like they flood broadcasts. So that multicast packet would be flooded to R2, R3, and R4. And now, because R1 is neighbors with all 3 of those routers, he would wait and he'd say, well, I need to get an EIGRP acknowledgement from R2, R3, and R4. So all of a sudden, here's R2, sends an EIGRP hello packet with the sequence number saying, I acknowledge. And he says, okay, R2, you're good to go. Thank you for acknowledging. And here comes R3 sending a hello packet, and we check that off. And then hopefully, eventually, R4 would send his own hello packet with that same sequence number in it. And so R1 would say, okay, all 3 of my neighbors have acknowledged this update. In the event that something went wrong and one of these routers did not send an acknowledgement, then R1 would resend his EIGRP update as a unicast packet directly to that neighbor. Okay, so what does that have to do with Ospf? Well, now remember that with Ospf, we saw when we were talking about the process of building a neighbor relationship, that it was important that all the Ospf routers who were neighbors had a common database, that their LSAs were the same. And so there were about 6 different steps we had to go through to get to that point. We had to go to init, two-way, exstart, exchange, loading, and then finally full to do all that. So in this type of an environment, in this type of a network where a router says, okay, there could be more than one router on this network. For example, think about Ethernet. The nature of Ethernet is that you can put one frame on the wire and you don't know how many people are going to see that. You don't know how many people are on that same Ethernet cable as you. The nature of Ethernet is that it could be 2, 3, 4, 44. You don't know. Ethernet is what we call a multi-access medium. So the designers of Ospf, they said, well, we could, on a multi-access medium like Ethernet, where there's a potential of lots of different routers out there on this wire, we could do like EIGRP does. We could have all the routers go through all 5 or 6 steps with each other. All the routers become fully adjacent. And they said, and then when an Ospf router sends out a link state update, we could do like EIGRP does, and all the other routers have to acknowledge it back. But the designers of Ospf took a different approach. They said, here's what we're going to do. On a multi-access network segment like Ethernet, we're going to have one router elected as a very special position, which is going to be called the designated router. Let's just say it's R4 as an example. During the exchange of hello packets is when this election takes process. So as these 4 routers are exchanging hellos, remember, their hellos are going out as multicasts. What's the multicast address that Ospf hellos go out to? 224.0.0.5. Hellos always go to that address. So inside that multicast hello, there are some fields that help these routers to figure out who this designated router is going to be. Well, what's the significance of the designated router? Well, once we know who the designated router is, router 1 will go through all 6 steps with router 4. Init, two-way, start, exchange, loading, full. Router 2 will become fully adjacent with router 4, and router 3 will become fully adjacent with router 4. But notice R1, R2, and R3, they're not becoming fully adjacent with each other. They see each other, they're still seeing each other's hellos because those hello packets are multicast, and so they're seeing that. But when they recognize, when R1 looks at R2 and says, oh, neither one of us is a designated router, we don't need to go beyond the two-way state. I see you and you see me, okay, good, we're in the two-way state, but that's as far as we need to go. We can stop there. But with the DR, everybody becomes fully adjacent. What's the purpose of that? Well, now if R1, let's just take R1 as an example. Let's say the R1 has a link state update that it needs to send, containing one or more new LSAs inside of it. R1 is going to say, I can only send my link state updates to OSPF neighbors that I am fully adjacent with, that I am in the full state. I went through those 5 or 6 steps with, which in this case is a designated router. He says, I know there's other routers here on this segment besides R4, the DR. How do I get this link state update just to him? Here's what I know I'll do. I'll send my link state update to a special reserved OSPF address of 224.0.0.6. Only the designated router is listening to that address. So now when this link state update packet goes in, it is a multicast, so it will be flooded. R2, R3, and R4 will see it, but R2 and R3 will discard it. They'll say, oh, I'm not a designated router, this is not for me. And so now that link state update will only be seen and processed by R4. Now R4 gets it. Here it comes in. Now R4 says, great, okay, my link state database is synchronized with R1. R1 and I are in sync. I got his link state. Oh, by the way, let me acknowledge that back. So R4 will do that. He'll send a link state acknowledgement packet back. Now R4 will say, but I have 2 other neighbors on this wire, R2 and R3. So now what R4 will do is he'll turn around and he'll send a link state update to R2 and R3, link state update. He'll reflect that link state update right back, going to 224.0.0.5. Now you might be thinking, well, wait a second. If R4 does that, isn't R1 going to see his very own link state update packet coming back to him? As a matter of fact, yes, he will. But remember, in that link state so that link state update has an LSA inside of it, maybe more than one LSA. Remember, every LSA has a field that says, who does this LSA belong to? Who created it? Who's the originator of the LSA? So in this particular case, when R1 gets that link state update and he looks inside of it, he'll say, oh, here's an LSA that was advertised by R1. Oh, that's me. Okay, I can ignore that. Here's another one that was advertised by R1. Oh, okay, that's me. I can ignore that. So in this regard, all these routers will become fully synchronized. So once again, just to repeat the process, the DR is elected. All these routers exchange hello packets, and within the hello packets are some fields, which I haven't talked about yet, which will help them to figure out who the designated router should be. Once that takes place, all of the routers become fully adjacent with the designated router. They go through all 5 or 6 of those steps with him. After that point, if anybody needs to send a link state update, they will send it to the DR, and they'll send it to 224.0.0.6. That is an address that only the DR is listening to. The DR in turn will reflect that link state update right back again so that all the other routers can get it, including the originator, who will say nope, and that will go to 224.0.0.5. So the idea being here is that if I have an Ethernet switch that, let's say, has 20 routers on it, they don't all have to become fully adjacent with each other. They only have to become fully adjacent with the designated router. They send their updates to him, and then they don't have to worry about it. He's the one who's going to turn around and reflect it to everybody else. So the designated router's job is to make sure that everybody is synchronized with everybody else. That is his job. Oh, and by the way, there's one other router here who is also elected as a backup designated router, or a BDR. Just like the DR is listening to 224.0.0.6, the BDR is also listening to 224.0.0.6. So when that initial update, when R1 sent his initial link state update to 224.0.0.6, both R3 and R4 got it. But it was only R4's job as a designated router to turn around and reflect that back so that in this case, R2 could get it. R3 is sort of just sitting there silently. He's taking stuff in because he's listening to .6, but it's not his job to turn around and reflect stuff back. Only if the designated router fails will R3 take up the job as the new designated router. So now that we know that, let's go into these slides. So a DR and a BDR are elected in broadcast and non-broadcast multi-access networks. Now we haven't really talked about those two terms yet. That's coming up in a little bit in a different video. But just think about it this way. We know that at layer 2, at the data link layer of the OSI model, there are several different encapsulation types. Ethernet, PPP, HDLC, frame relay. You could probably think of 1 or 2 or 3 more in addition to that. What's one thing that makes them different from each other? Some of those encapsulation types were built around the assumption that I could put one frame on the wire and multiple devices could see that one frame. Like Ethernet, right? That's the nature of Ethernet. That's the nature of, well, let's just stick with Ethernet. That's Ethernet. You can put one frame on there and everybody will see it. Other layer 2 encapsulation types say, well, if I put one frame on the wire, it's only going to go one place, like the point-to-point protocol or HDLC. Those are layer 2 protocols that say this was designed for a cable that's just got 2 devices. Put something on the cable, it only goes over here. This guy puts something on the cable, it only goes over here. So there's really no need for an address because there's just the 2 of us. PPP and HDLC are like that. And then there's other types of encapsulation types like frame relay that say, well, this particular cable could go multiple places. For example, think about your connection to the internet. You're sitting at home, you have a connection to the internet. That one cable you have leading out of your house can reach billions of remote destinations. So it's sort of like Ethernet that way. You could put one thing on there, one cable that gets you multiple places. But is it possible for you to put something on that cable that all those remote destinations are going to see? No, it's not. In the case of your internet connection, you have to address everything you put on that cable to who you want to send it to. It doesn't support broadcast. You can't put a broadcast on your cable modem or your DSL connection to Time Warner Cable or Comcast and expect that all the billions of devices in the internet are going to see it. It doesn't work that way. So that's what we consider a non-broadcast multi-access network. But in all these networks where I can put something on a cable and I can say to myself, well, there could be more than one device reachable on this cable. In that particular case, a designated router and a backup designated router will be elected. And we've talked about these last 2 bullet points right here. Okay, so how do we determine which router that will be? Well, by default, the very first router that comes online on a cable will be the designated router. That's pretty much it. Now, if 2 routers come online at the same time, if they start exchanging hellos at the same time, then the router with the highest interface priority will become the designated router. And this is the first time I've talked about this. So in Ospf, when you use the network command under Ospf, and Ospf says, oh, here's an interface right here that falls in line with that network, I'll start speaking, I'll start sending out hello packets. Well, on this interface, he gives it an Ospf priority value. It's actually the value of 1 by default. And so in my hello packets I send out, that's one of the things I put in there is what my interface priority is. So if I'm sending hello packets to you and you're sending hello packets to me, if one of us has a higher interface priority than the other, we're done. The highest interface priority will win, and that will become the designated router. And when you do the command show IP Ospf neighbor to view your neighbors, you will see on like an Ethernet segment, you'll see at least one neighbor shown as DR for designated router, possibly another one that says BDR, and then others that will say DR others. So DR others mean routers that currently are not the DR, not the BDR, but they could be in the future. If the DR and BDR fail, these other routers could potentially become designated routers. Now, let's say that you have not manually configured the interface priority. And remember, it's interface priority. It's not a global priority. So on a router, if he's got 5 interfaces, if you wanted to, you could have each interface have a different priority value. But by default, they'll all be the same. They'll be the value of 1. Well, if you and I exchange OSPF hello packets over an Ethernet segment and we both have the exact same interface priority, then we're going to compare each other's names, our router IDs, our OSPF router IDs. And whoever has the highest router ID will be the winner. That will become the designated router, and the second highest will become the backup designated router. So a lot of times people don't really necessarily care which router will be the DR or the BDR. They just let OSPF take care of that by itself. But let's say you want to have some control over that. As the network administrator, you want to be in control over which router was going to become the DR and the BDR. Well, the easiest way to do that would be to go to the interface and change the OSPF interface priority. And in a video coming up where we actually go over the configuration commands, I'll show you how to do that. The second way you could do it is by manipulating the OSPF router ID itself. So as soon as you type router OSPF and then some process ID and hit enter, it elects a router ID for itself. It looks at all of its interfaces and says, I need to pull an IP address here and use that as my name, as my router ID. So what's the order? How's it going to do that? Well, number one, first thing OSPF is going to say is, all right, under my configuration, under my router OSPF configuration, did some human being actually type the router-ID command? If they did, that's what I'll use as my router ID. What if you did not type the router-ID command? Well then, the router will look to see if you have any loopback interfaces. If you do, whatever the highest IP address is of all of your loopbacks, that will be your router ID. And then lastly, if there are no loopbacks and there's no OSPF router ID that was manually configured, it'll just look around at your interfaces and select an IP address from your interface, the highest IP address from among your physical interfaces, and use that as its router ID. Now, interesting little factoid here. A lot of times people think, oh, well, only interfaces that are actually up are candidates for the router ID. That's not actually true. Even an interface that is up-down or down-down is a candidate for router ID. The only time there's an IP address on an interface and OSPF says, I can't use that, I can't even consider that, is if the interface is administratively disabled, if it is shut down. Other than that, the IP address could potentially be used as the router ID, depending on if it's not a loopback and if it's the highest IP address on the box. So that ends this video on the OSPF designated router and backup designated router process.